Okay, let's see where we are here. All right, so I think 8.3, we're going to look at the idea of conditional probability. So let's see, to begin to talk about this a little bit, all right, let's suppose that you want to find the probability of an 18-year-old or older having lung cancer. So would the probability be high or low? Well, we hope low. The probability of anybody getting cancer is generally low at a young age and increases as you get older. But what if you wanted to find the probability of an adult having lung cancer, given that they're a heavy smoker, like they smoke like 5 packs of cigarettes a day? Yeah, the probability would change and it would go up. Okay, so this example is what we call conditional probability. We notate this like this. This would be the probability of getting lung cancer given that you're a heavy smoker. So that would be L is lung cancer, the bar is given, and then that would be given they're a smoker. So you write that conditional probability like that. Okay, I'm going to go over this problem. This is kind of a good illustration of this. This says, what is the probability of rolling a prime number on a single roll of a fair dice? Okay, well, we can figure that out pretty easily. The prime numbers are 2, 3, and 5. So out of this sample space of 1, 2, 3, 4, 5, 6, there's 6 things that can happen when you roll a 6-sided fair dice, and 3 of those are prime numbers, so that would be a 1/2 probability. Okay, now the question becomes now, what is the probability of a prime number coming up given that an odd number turned up? So what I'm doing is you're rolling the dice, and I'm telling you that it's an odd number. So the question is, since I'm telling you it's an odd number, what is the probability that it's prime? Well, that's not 1/2 anymore, it's different. So the idea on this is like this. I'm giving you that it's an odd number. So basically, this sample space changes like this. So we're going to say, let's notate this like this. We would say it's a probability, not like that. Let's use P for probability. And we're going to look at the probability of getting a prime number given that it's an odd number. Okay, well, what we end up doing on this is kind of this. You end up just looking at the odd numbers only. I'll show you 2 ways to do this. So there's 3 odd numbers. How many of those are prime, though? The 3 and 5 is. So out of the odd numbers, 2 of those prime, so you would expect to get a 2/3 probability. The way that you work this out, let me show you how you're going to do these type of problems, is it turns out that what you do is you look at the probability of the prime intersect with the odd numbers, and then you look at, as your sample space, the probability of odd numbers. And in a sense, that's what I just did right there. So the probability of getting an odd number is 3 out of 6. There's 3 odd numbers out of the 6 possibilities. The probability that it's prime and odd would be this. So the idea with that would be prime numbers intersected odd numbers would be just the 3 and 5. So the intersection between odd and prime numbers is 3 and 5. Okay, so that would be a 2/6 probability like that. Okay, well, what happens is the 6s would divide out, so you would get a 2/3 probability. So what you're really doing is you're given that there's 3 odd numbers. How many of those are prime? 2 out of 3. That's what we mean by a given probability. Okay, that's a good illustration to get you started on the concept of a given probability. Now, the formula that we follow is what I just did. If we're going to do the probability of A given B, we do the probability of the intersection, and then we divide by the probability of that given part. And of course, the probability of B has to be some positive number. It can't be 0 because you can't divide by 0. So that's what I did in this problem, is I did the probability of the intersection of prime and odd numbers, which there's two numbers that are prime and odd out of 6. Then I divide it by the probability of it being odd. There's a 3/6 probability of the dice turning up odd. Okay, so that's how you work out given probabilities. Okay, so on the next page, we're going to look at a probability diagram here. And first of all, I want to explain how this is set up. So this is your pointer right here. And it's a little bit hard to see on here, but these things are not equally likely. So for instance, this 5 could be further subdivided into 3 things. The 6 can be divided into 2 pieces, and so can the 2. So the way this works out, really on this, the way the probabilities are done is based on the area here. So the probability of getting a 2 is 0.2, because if you counted this out, I'd really be subdividing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get them all equally likely. Probability of getting a 1 is a 1/10. Probability of getting a 2 is a 2/10 because it takes up 2 of those sectors, see, like that. Okay, probability of getting a 3 is 1/10. Probability of getting a 4 is also 1/10. Now the probability of a 5, see, you can break this up into 3 pieces the same size as the rest, so that would be 3/10. And then finally the probability of getting a 6, that's subdivided into 2 parts, so that's 2/10. Now I'm giving those probabilities to you, so what I'm saying on this is this spinner, these things are not equally likely. Okay, that's the idea, because some of the regions are bigger than the others, so that's the idea. Okay, so what we're going to do on this one, first of all, is we're going to do 2 parts of this. Part A says, what is the probability of the pointer landing on a prime number? So what we're going to do is the probability of a prime, and we're going to work that out then. So really what that is that's just the probability of getting a 2 or a 3 or a 5. And remember, when we do OR probabilities, we add them together, okay? And there's no overlap between 2, 3, and 5, so these are disjoint sets. So what you would do is you would do the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 5. You have OR probabilities, you're doing a union. So now if you look this up on the table, it would go like this. The probability of getting a 2 is 0.2. Probability of a 3 is 0.1. Probability of a 5 is 0.3, so we would just add up 0.2 plus 0.1 plus 0.3, so that probability would be 0.6. Okay, so that would be the answer to part A. All right. Okay, so the next thing we're going to do is, now it's a given probability. It says, what is the probability of the pointer landing on a prime number given that it's an odd number? So when we do this, we'll write this as probability of prime given that it's an odd number. So you notate that with that bar like that then. Well, what you have to do is you have to apply this formula. So it goes like this. I'll show you a couple of ways to figure this out. First, we're just going to use the formula. So we're going to do the probability that it's a prime intersect odd divided by the probability that it's odd. So that's what we have to basically work out on this problem. So first of all, let's figure out what the probability is that it's odd. Okay, well, the odd numbers are the 1, the 3, and the 5. So we would have to add up those numbers there to get that probability. So that would be 0.1 plus 0.1 plus 0.3. Okay, so we would get that. So of course that would add up to 0.5. All right, so we got that. Now what we're going to do is we're going to do the probability that it's prime and odd at the same time. Okay, well, let's see. Let's identify the things that are prime. So the prime numbers are 2, 3, and 5. Okay, now what we're doing is the intersection of those. Okay, so that's it. Those are the prime numbers, is the 2, the 3, and the 5. Well, where did the colors blend and turn green? The intersection would be 0.1 and 0.3, see. So what we'd end up getting is the 0.1 plus the 0.3, like that. I'm going to do that one more time so you get 0.4 over 0.5. So let me show you how I did this again. So what I did was I highlighted the prime numbers. Okay, the prime numbers are, and I'm going to highlight just the probability. Whoops, 2 is not a, yeah, 2 is a prime number. So we've got the prime numbers are 2, 3, and 5. Now I'm going to highlight the odd numbers in blue, so that would be 1, 3, and 5. So see where they overlapped was right there. Okay, so that's how you do that. Well, okay, what happens on this probability is really what you're doing is multiplying, you're moving the decimal over 1 unit. If you multiply the top and bottom by 10, you get 4/5. You don't have to show that you're multiplying by 4/5, but that would give the probability, and then if you wanted to do a decimal, you would get 0.8. So notice the probabilities changed from 60% to 80%. So what I'm doing is I'm telling you, hey, guess what? The spinner landed on an odd number, so the probability of it being prime is a higher probability than just the probability of it being prime, because I'm giving you that it's an odd number. Okay, so that's how you calculate and put that together. Okay, all right. Down at the bottom of the page, we're going to look a little bit at how these go together now. And I'm going to pause just for a second here. It won't affect you, though. Okay, so let me read off, kind of familiarize yourself, first of all, with what this chart is saying. Okay, so this is data about a driver being in an accident on the last day of the Memorial Day weekend. You'd expect accidents to go up on Memorial Day weekend for a couple of reasons. Number one, there's more drunk drivers. Number two, there's just more people on the road. Okay, people are out partying and stuff, so the likelihood goes up. Okay, unfortunately. So the idea is this is the probability of having an accident, is this number here. So regardless of whether it rain or no rain, the total probability of having an accident is 0.040. The probability of not getting an accident is high, which we would hope, about 96%. So notice those two numbers add up to 100% like that. Okay, then this says this is the probability of rain. This is the probability of not rain, so that's 100% like that. So always this row and that column both add up to 100% like that. Okay, so what this is saying is the sample space would be rain and an accident, rain and not an accident, no rain and an accident, and no rain and no accident. Okay, and that's what this is doing. So basically this is the probability of rain and an accident. This one is the probability of rain and no accident. Okay, like that, and so forth. Okay, so I'll make sure that everybody kind of knows what these sample spaces are. Then this one would be the probability of no rain and an accident. And then finally, this one would be the probability of no rain and no accident. Okay, like that. So those are the 4 individual parts that you would put in a Venn diagram, basically like that. Okay, so we're going to work out each part of this. So part A is the probability of an accident, rain or no rain. So we're looking at the probability of getting an accident with rain or no rain. Okay, so I'll kind of show you how we're looking at that. So the idea is the probability of being an accident is these numbers right here. Okay, regardless of whether you have rain or no rain, so it would end up being this right here, right? So that's the probability of being in an accident. Rain or no rain, that would be a total of 0.040, okay? So that's just basically being in an accident or rain or no rain, okay, like that. So the way you would do that is just add up those two probabilities. You'd have 0.025 plus 0.015, so that would be a total of 0.040. That's what this is saying, is that's the probability of being in an accident regardless of whether it rains or not. So that's what that one is saying. Okay, part B is saying what is the probability of rain, accident or no accident. Okay, so what this one means is this. I'm going to write this like this: probability of rain or an accident or no accident. So you just got to read the table right. So what this means is this is the probability of rain. That total probability is 0.360. So that's the answer to the problem. It's just the probability of rain and no accident is this. The probability of rain and no accident is that. So you just add up those two. Okay, like that, and you would get a total of 0.360. So that's what that one means. Okay. Part C says find the probability of accident and rain, and being the key word. So we're looking at the probability of being in an accident intersect rain. Okay, it's an and probability, so that's what we're doing. So what I'm going to do on this is I'm going to highlight being in an accident. Okay, and I'm just going to highlight those two numbers right there, not the total. I don't worry about the total. Then I'm going to highlight the probability of rain. So what's that? So where did they intersect? There you go, 0.025. You can see where the colors blended. So that again is an intersection. So that's 0.025. There's nothing to calculate. Okay, and then the next one is the probability of an accident given rain. Okay, so this is where we now have to kind of put together our formula here. So let's write down the formula. If you're doing this, you would have to do the probability of being in an accident and it raining, which we just did in part C, divided by the probability of rain. So that's the formula. You do the intersection and then divide by the given part, the second part. Okay, so the probability of being in an accident and rain is 0.025. The probability of rain is 0.360. That's the grand total. So basically, you would just crunch this out. And again, you can move the decimals over 3 places. You have to move the decimal over the same amount on both. So you'd get 25 out of 36. And if you wanted to take your calculator and change that to a decimal, 25 out of 36 would just be this approximately. I'll round to 3 digits, and that'll be about 0.694. So it's about a 69.4% chance of that happening. So that's how you would do the given probability, is when you see the question about a given probability, you immediately need to think of that formula. You don't need to think of anything else. It's just, I need to apply that formula correctly for a given probability. Okay. All right. On the next page, you're going to work quite a bit with some given probabilities. I'm going to pause this for a minute and put up my card diagram. Okay. So just keep the video rolling. Ta-da, it just pops up like magic. Okay, so here's what we have. We're going to do a bunch of given probabilities. Okay, we're going to be talking about drawing a single card from a 52-card deck. So what we're going to do on this one is we're going to do the probability of getting an ace given that it's a heart. So I'm just going to write this like this. Okay, you get an ace given that it's a heart. Okay, so this is going to go like this. The formula would go like this. It would be the probability of getting a card that's an ace and a heart at the same time, divided by the probability that it's a heart. So you want to start by just doing your formula. Okay, how many cards are ace of hearts? Okay, well, there's only one. That would be the card that is an ace and a heart at the same time. So that would be a 1 out of 52 probability. Okay, the probability of getting a heart would be this right here. There's 13 hearts in a deck. You don't worry about the intersection or anything. You just follow the formula. So there are 13 out of 52 cards are hearts. So you do the ace of hearts. There's only one ace of hearts, and that's the intersection between aces and hearts. And then you just do the probability of hearts. That divides out. So you end up getting a 1 out of 13 probability. That's the answer of that problem. Okay, so again, apply the formula on these given probabilities. Okay, the next one is the card is a heart given that it's an ace. So we're doing this backwards. So let's see if it's the same. So it's a heart given that it's an ace. Okay, so the formula would be probability of heart intersect ace all over the probability of an ace. Now, since the probability of an ace is different than the probability of a heart, then you're going to expect to get a different answer. So heart and ace. Okay, there's only one card that's an ace and a heart at the same time. So that is a 1 out of 52 probability. But the probability of an ace is how many aces are in a deck? There's 4. So that would be a 4 out of 52 probability. 52s cross out, so therefore you would get a 1/4 probability. Essentially, you got to figure out these two probabilities right here. Okay. Okay, the next one says the probability that the card is black, given that it's a club. So according to this, we would do, the formula says we would do the intersection of cards that are black and club at the same time, divided by the probability of something being a club. So let's crunch it out, and then we'll talk about if the answer makes sense to you or not. If you understand cards, you could tell me what the probability is without thinking about it too much. Okay, so it's got to be the intersection of black and clubs. All right, so it's basically like this. Those are your clubs. The black cards are that row and that row. So where did they intersect? They intersected here. So there's 13 cards in a deck that are black and clubs at the same time. So that would be a 13 out of 52 probability. Okay, all right. Now I'm going to erase that and start over again. Now the question becomes, what is the probability of getting a club? Well, there's 13 clubs in a deck, so that probability would also be 13 out of 52. So you get 1. So you get an event that's absolutely certain to happen. I want you to think about this for a minute. You draw a card out of the deck, and I tell you that it's a club. Couldn't you be 100% certain and tell me, oh, that card's black? I mean, that's what it means. I'm telling you it's a club. You're saying, yeah, it has to be black. Okay, that's why it's certain. Okay, so that's the idea. All right, so let's see. Let me have you guys do some problems and see if you're absorbing this information the way I'm hoping you are. So I'm going to move this down and let you do these problems. There's 3 problems that I want you to do on this page then. So let's just do these 3 problems. Go ahead and pause video, resume when you're ready to check your. Okay, so here's the answers that you should have got. Problem number 1, you should have got a half. Problem 2, 3/13. Problem 3, 1/2. So let me run through how I work these out then. Okay, so the idea with this is, with this first one, is it's going to go like this then. Oh, hold on. Okay, so this one kind of works out like this. Oh, that stupid control thing come up, and I never know how to get rid of that. Sometimes it just kind of fixes itself, so hold on just a second. Okay, I never know why that happens, but it happens sometimes. Okay, so here's what happens. We're doing the probability of a red card given it's a face card. So we do the probability of red intersect F divided by probability of the face card. So first of all, the face cards, I'm going to highlight all of the face cards. So there's 12 face cards, so that's a 12 out of 52 probability there. Now what you got to do is how many of these face cards are red? Well, okay, there are 6 of those face cards that are red. So the intersection between red cards and face cards would be these 6 here. So that's how I get that 6 out of 52, like that. Okay, what happens is the 52, whoops, I'm on the wrong problem. Come on, teacher. Okay, so we got that. That's 6 out of 52. The 52s cross out. 6 out of 12 is 1/2. Okay, so that's how we do that. All right. Okay, all a matter of identifying clearly what the set is that you're trying to count. So this one is backwards, the probability of a face card given that it's a red card. So the probability of a red card would be there's 26 red cards in a deck, so that would be a 26 out of, that should be 52 there. Okay, so we got that. Don't reduce the fractions until the end of the problem. And then we're looking at that it's a red face card. So the red face cards, again, were these. Okay, so that would mean out of these face cards, 6 of them are red. So that's a 6 out of 52 probability. Okay, so see what you're doing with that part is you're doing the intersection of the 12 face cards with the red, and that would be this right here. Again, 52 crosses out, 6 over 26. Reduce the fraction, so you get 3 out of 13. Okay. Okay, so the next thing we would have is on the last problem I had you do, this one said the probability that it's a red card given that it's a jack should get a half on that. The way I look at that is, you draw a card, I'm telling you it's a jack. Isn't there a 50-50 chance it's red? Okay, if you understand what I said, then the problem should make totally good sense to you. All right, so what you do is probability that it's a red intersect jack. So red cards intersect jack would be this. There's 2 cards in the deck that are jacks that are also red, so that's 2 out of 52. The probability of a jack is there's 4 jacks in a deck, so you have that. Again, what happens, 52's cross out, 2 4s reduces to a half. So that means you have a card in your hand, I'm telling you it's a jack, I'm asking you, what is the probability it's red? Well, half of the jacks are red. All right, so that's how you get that. Okay, moving to the next part here, we're going to begin to look at the product rule a little bit. Okay, so I'm going to look at the the product rule, and I want to show you where this comes from. So I'm going to show you this formula and where it comes from. So this is kind of a derivation of this formula. It's good to know where these formulas come from. So you should write this down maybe up here at the top or something. I'm going to do this in 2 different ways. So what we just learned is the probability of A given B is the probability of A intersect B over the probability of B. Now, if I did that given probability backwards, if I did the probability of B given A, then it's still the probability of the intersection. And it doesn't matter which order you do an intersection, it's the same thing anyway. But then it would be divided by the probability of A. So you always divide by that, the given part. Well, what you have here is you have a mathematical equation. So if I multiplied both sides of this equation by the probability of B, then I would get this formula right here. This would say the probability of A intersect B is the probability of B times the probability of A given B. So there's really 2 forms of this formula. You would get probability of A given B equals probability of B times the probability of A given B. So that's one formula. If you take this formula, which is just doing this backwards, it is different. You have probability of B given A is probability of A intersect B over probability A. So now if you multiply by probability of A, then you get a slightly different formula, but it'll give you the same answer. So you end up getting the probability of A intersect B is equal to the probability of A times the probability of B given A. So either one of those things will work and give you the intersection. That's where that formula comes from. So if you're doing a probability of an intersection of 2 events, and you have a given probability built in there, then you can use this to compute that probability of A given B then, okay? So what I'm going to do on a couple of examples, I'm going to do an example 2 and read this to you and see if you can kind of put this together. So let me read this first of all. It says, if 60% of a department store's customers are female, and 75% of those female customers have credit cards, what is the probability that a customer selected at random is female and has a store credit card? All right, so what we're really doing on this particular problem then is we're doing the probability they're a female and they have a credit card. So that's what we're going to find, and that's a set intersection. So we're going to be using this formula that we have up here then. So let's identify our sets, okay? So first of all, let's let S be the sample space, and that would be all store customers. So you want to write all this stuff down so that you can, when you're referring to how I'm doing this, if you need to, you'll know what everything represents. The other thing we have is F is the female customers. Okay, and the other thing is this has to do with credit cards. So C is going to be the customers with credit cards. Okay, so that's kind of what we have in the problem. All right, now what we're going to do is the question on this is this. What is the probability that a customer is female and has a credit card? So what that means is it means probability that you're female intersect you have a credit card. All right, so according to this formula, what you'd want to do on this is you would want to apply this formula. You have to apply one of these formulas right here. Now, what we have is we have the idea that we know the probability that they have a credit card given that they're female, because it says 75% of the female customers have a credit card. Okay, so as I put this together, I'm going to write a couple other things on here. Over here, the probability of being female is 60%. Okay, so there's 60% of these customers are female, so I'm going to write that as 0.60. The other thing it says is out of the female, 75% of the female have a credit card. So we would write this like this. This would be the probability that they have a credit card given that they're female. Okay? And that would be the 75% like that. All right? So that's the way I look at that. Not the other way around. It's not the probability that they're female given they're a credit card. It's the probability they have a credit card given they're a female, because we only know about they're 60% female in here. Okay? So according to this formula, what you end up doing, if you look at this formula right here, you're going to have to use this one right here. So we're going to do two things. We're going to do the probability they're female, so we know that, multiplied by the probability that they have a credit card given they're a female. See, those are the two things that you have given in this problem. So the probability that they're female is 60%. The probability that they have a credit card, given that they're female, is 0.75. Then you could take the calculator and multiply those two numbers out, and then you would have the answer of the problem. So 0.60 multiplied by 0.75 will give you that probability. So I think that's 0.45. Or you could write that as about 45%. Okay? All right. So that's how you would do that. I want you to start looking at the next problem. Okay, got some cooking going on here. Okay, so let's see. You're going to be using the same thing. I'm going to kind of help you with a couple of things on this. So first of all, in this problem, it says 80% of the male customers have credit cards. So a couple of things. We're still going to have these same things. We still have S is all the store customers. Now we have M is the male customers. And we still have C is still the customers with credit cards. Okay, so what you want to do on this is first of all, the probability of female is 60%. Okay, so you want to figure out the probability of being male. So you need to figure that out. I'm just going to help you kind of think through how to start this problem. So you need to figure this out. Okay, the other thing you got to do is you need to figure out this. So you need to figure out the probability that they have a credit card given that they're a male. So you're going to need to figure those two things out then when you do that. Okay. All right. And now you want to think about the formula. So what we're doing with this is it says, what is the probability that it's a male and they have a credit card? So what you're looking for on this problem is probability male and they have a credit card. So you want to figure out how to put that together with those two given probabilities then. Okay. So remember, this goes to the same problem. It says 80% have credit cards. So if you can figure out these two probabilities, then you can put this together. Okay, so I'll give you a few minutes to do that. Pause, check when you're... Okay, so this is what you should have done. first of all, remember in the previous example, 60% female. So we're assuming two genders here, okay? No transgender here, just male, female is what we're assuming, okay? So we got 1 minus 0.60, and we have 0.40. So there's 0.40, 40% males. And then the problem said 80% have a credit card given that they're a male. So what you do is to figure out this and probability, you're doing the probability that it's a male and at the same time they have a credit card. So you do the probability of male times probability that they're a male given they have a credit card. So you multiply those two probabilities together, so you get about 32%. Okay, so that's how you would utilize that formula to figure that out then. Okay, questions? Okay, when it's a given probability, you have a formula for a given probability. When it's a and probability and you have one of the given probabilities, something given something, then you're going to use this formula, okay? All right, next page, what we're going to do is begin to get into probability trees. So let me go over this a little bit then. All right, so this problem says that you have two balls are drawn in succession without replacement. And that's a big deal is what I mean by without replacement. From a box that has 3 blue and 2 white balls, what is the probability of drawing a white ball on the second draw? So the first thing that I'm going to do on this, let's just draw like a container here. And we're going to have, let's see, it says we have 3 balls that are blue. So I'm going to highlight, those are the blue right there. And then we have 2 that are white. Okay, so we got 2 of those. You just want to draw a diagram so it's clear what you have. All right. Okay, what we're going to do is we're going to draw what we call a tree diagram to kind of help us with this. So we're going to define this like this. I'm going to say, since we're looking for the probability of a white on the second draw, I'm going to write this kind of like this. W1 is going to be white on first draw. W2 is going to be white on second draw. And then we'll have B1 will be blue on first draw. And B2 will be you get a blue on the second draw. Okay, so that's what we have to begin with. All right. So to figure this out, you got to look at a probability diagram, and a tree will kind of help you figure this out. It's pretty hard to do this without that. So the first thing we're going to do is we're going to do this probability tree. So we're going to make the tree. And the tree kind of goes like this. Okay, we're going to start somewhere. And what's going to happen is we're going to branch out in 2 directions. On the first draw, 2 things can happen. Okay, we either get a white ball or we get a blue ball like that. Now what we're going to do is we're going to look at this probability diagram to figure this out. So right now, tell me what the probability of reaching in there and getting a white is. There's 2 white out of 5, so that is a 2/5 probability. Okay, tell me what the probability of getting a blue is. Good, 3 out of 5. Notice 3/5 and 2/5 equals 1. Okay, so we have that. Now we're going to move on to the second draw. So we branch out into 2 directions. We could either get a white on the second, or we could get a blue on the second. Same thing here. We could either get a white on the second, or we could get a blue on the second like this. Okay, now we're going to talk about what the without replacement means then. So here's kind of what happens on this. This right here, this probability right here is really this. It's a probability of getting a white on the second draw given that you got a white on the first draw. Well, if you got a white on the first draw, now I want you to just kind of watch how I do this. So if I take a white out and I don't replace it back in, then the probabilities change. So what's the probability of getting a white now? Okay, good. It's 1 out of 4. So that's a 1/4 probability like that. That's what that means. Okay, now I'm going to just kind of start over again and put that thing back in. Now this probability here, that's the probability of getting a blue on the second draw, given that you got a white on the first draw. So let's take the white out. We got a white on the first draw. What's the probability of blue now that the white's gone? Okay, that's 3/4. Good. Okay, so we have a 3/4 probability there. Notice a fourth and 3/4 adds up to 1. Okay. All right, let's put that white back in. Okay, now what we're going to do is go down here. So this is really the probability of getting a white on the second draw, given that you got a blue on the first draw. So what we do is let's take out a blue and don't put it back in. That's what the with replacement means. So that would mean the probability of getting a white now is 2 out of 4. The probability of, and then this next one goes like this. Now, this probability right here is saying the probability of a blue on the second draw, given that you got a blue on the first. So it's the same thing. We took a blue out. We didn't plug it back in. So there's 2 out of 4. So you'd have a 2/4 probability like that. Okay, so that's what you got to understand about the idea as with replacement is different than without replacement. Without replacement means you take the ball out, you don't put it back in, so the sample space changes in the second step. Okay, so anyway, that's what we have. So we kind of figure out all these things now. So now we're ready basically to put this whole thing together like this. So step 2, what we're going to do is there's a couple of things that we need to do. It says, what is the probability of drawing a white ball on the second draw then? So I'll kind of end up showing you a little bit of a shortcut on this then. So what we're ultimately doing on this is finding the probability of a white ball on the second draw. So here's what you want to look at, okay? If you're going to get a white on the second draw, there's 2 ways to get there. One way to get there is to get a white one, then a white on the second, okay? So that would mean that what we would have is we'd need to figure out the probability of getting a white on the second, given that we had a white on the first. Well, that would be the product of these 2 probabilities, so that would be 2/5 times 1/4. That would be 2/20. Okay, and I'm not going to get a reduce until the end of this problem. Okay, the next thing we'd have to do is the other way to get a white on the second draw is to go this route. Okay, you would have basically this probability. You would have the probability of a white on the second, given that you had a blue on the first. Well, that would be these 2 numbers, 3/5 and 2/4. So if you take 3/5 times 2/4 and go straight across, you get 6 out of 20. Okay, so it would go like that. So there's 2 ways for that to happen. You don't consider, anything other than these 2 branches on the probability tree. So in step 3, this is where we start kind of putting it all together then. We've already figured out all these probabilities. So basically the probability of a white on the second draw is going to end up being this. It's going to end up being the probability, again, of getting a white on the second, given white on the first, plus probability of getting a white on the second, given that you had a blue on the first. So those 2 probabilities, we already got them. This one was 2 out of 20. This one was 6 out of 20. So you end up getting 8 out of 20 is your probability. You can now reduce that fraction by a factor of 4, and you would end up getting the probability of 2/5 would be the answer of that probability. Okay, that's it. The probability tree is the way to put that together because it's really hard to visualize what's happening on that problem. Okay, I'm going to let you try a problem. It's almost the same thing, except it's a little bit, this time you have 4 red and you have 2 white. So I'm going to scroll down here and let you put this one together and do the probability tree. So I would start by just kind of drawing, this is your bag, and you're going to have 4 red this time, and you're going to have 2 white. So just repeat what I just did, draw your probability tree, and then see if you can figure that out. Okay? Go ahead and pause the video and come back and check and see if you're right. Okay, so if you want to check here, the answer you should have got was 2/3. So I'll kind of talk through what I did if you didn't get that. So the first thing I really wanted to see on this is the probability tree. So I'm going to let R1 be red on first, R2 red on second draw, W1 white on first, W2 white on second. So when you start this, you got two choices. Either you get a red or you get a white. At the beginning of the problem, there's 4 red out of 6, so that is a 4/6 probability. The probability of getting a white at the beginning is 2 white out of 6. And again, notice 4/6 and 2/6 add up to 1. Okay? Then it goes like this. We're going to look at, we branch out to a red on the second, white on the second. So if we already got a red on the first draw and we don't put it back in, then we're down to this. Now the probability would be 3 red out of 5. The probability of white would be 2 white out of 5. So 3/5 and 2/5 is what you get there. Okay. Remember, you take out the red like that, and then you redraw, but you don't put it back in. Okay. The next part from the white one, you should have branched out into R2 and W2. Now we're taking out a white. So let's say we got a white on the first draw. The probability of red now is 4/5. The probability of white now is 1/5. So you take it out and don't replace it like that. All right, so that's kind of how you do that. Now we do the probability like this. The question was, what is the probability of getting a red ball on the second draw? Well, there's 2 ways to get this. Okay, you can either go there or there. The only way you can get to R2 is to go through this and then go through that. The only way this way is to go through this and go through that. So what you would do is you're really doing the probability of getting a red on the second draw, given that you got a red on the first. So that's 4/6 times 3/5. The other way is the probability of red 2 given white 1 would be 2/6 times 4/5 like that. Okay, multiply this out, that's 12/30, that's 8/30. Add the probabilities together, you get 2/3. Okay, so you're just looking, you got to look at that tree diagram, and there's 2 ways to get to red on the second draw. So that's how you put that together using that formula. Okay. All right, so pause if you need to look at that and absorb that a little bit. It's not hard to do. Okay, let's see. Now the next thing is, this kind of explains probability tree. This is what I just explained to you. So you can read over this if you want to. I'm not going to read that to you. Then I'm going to go down to this example 4 and crunch this. Okay, so let's read this example 4. Now we're going to do this with a probability tree, and we need to kind of carefully read what's going on this problem. So let's see. To begin with, let me just read this. So it says an auto company A subcontracts the manufacturing of its onboard computers to 2 companies. 40% go to B, 60% go to C. I'm just going to pause right there because that's a key piece of information. I'm going to try to color code this. Then it says company B turns around and subcontracts 70% of its orders to company D and the remaining 30% to company E. Okay. Then it says this. Then it says the onboard computers are completed by companies D, E, and C. They are shipped to company A, and it's been found that these are defective for D, E, and C. Now, you got to read through this a couple of times to begin to appreciate what's happening. And then it says, what is the probability that a given onboard computer will be defective during the 3-year warranty period? So starting over again, it says company A subcontracts its manufacturing of computers. 40% go to B, 60% to A. So we're going to do a probability tree. We're going to start with company A. And again, we're going to subcontract this to company B and to company C. Okay, like that. Now, these are individual probabilities here. So this is 40% goes to company B, so I'm going to put a 0.40 there, and 60% subcontracts to company C. Again, those add up to 100%. So that's the part I have kind of highlighted in yellow. Now, if you read on, what it says is it says company B subcontract 70% of its orders that it got from A to D, and then 30% to E. So from B, you're going to subcontract to D, and you're going to subcontract to E. The individual probabilities are, let's see, it says 70% go to D, then it says 30% go to E. So again, those things add up to 100% like we'd expect. Okay, now if you read on a little further, okay, then it says, let's see, the onboard computers are completed by companies D, E, and C. So that's all done now. They are shipped to company A to be used in various car models. It has been found that 1.5%, 1%, and 5% of the boards from D, E, and C are defective. So what we're going to do is we're going to branch out from each of these. So if we branch out from there, the boards are either okay or they're defective. Okay, and we're going to do the same thing here. From this, same thing, branch out. Some of them are okay, the rest are defective. Same thing here. Some are okay, some are defective. Okay, so let's put this together now. The probabilities say this, and they're kind of saying in order. So this one, 1.5% from D are defective. Okay, so that would be 0.015 is what that would be. So I'm going to put the 0.015 there, like that. Then it says 1% from E are defective, so 1% is 0.01. Okay, then finally it says 0.5% come from C are defective, so 0.5, move the decimal over 2, you would get 0.005 like that. So that's what those numbers are, is that right there. Well, you can figure these out pretty easily then. So basically what goes here is you would do 1 minus 0.015. What goes here would be 1 minus 0.01, and what goes here would be 1 minus 0.005 like that. So you can use your calculator if you need to do that. And I don't have to give you what both are because you subtract from one to get the other one like that then. So I'll do 1 minus 0.015, and that will give, this part right here is 0.985. Okay, same thing here. If I do 1 minus 0.01, that'll be 0.99. Use your calculator as you need to. Okay, and then the last one would go like this. We'll do 1 minus 0.005, and that will give 0.995 like that. So that's the probability diagram that we need to put together in order to answer this question then. Okay, so that would be the calculations you would do. So that's the first thing that you want to do on the problem, is start that way then. Okay, now what we're going to do is try to put the basic probability together. So what it says on this is, let's read the question. It says, what is the probability that a given onboard computer will be defective? So what that means is there's 3 ways to get a defective computer. That's this way, or this way. So what you're doing is you're going through these branches like this. Okay, the way to get here is to go through this, through D, and through B. So that's your first probability that you would do. So when we put the probability of a defective, we would have 3 individual probabilities we would have to do. So that would be this branch. So that would be 0.40 times 0.70 times 0.015, like that. Okay, the second way to get this, to get defective, is to go through this, this, and this. So you got to go through E and through B to get to that branch like that. So that would be plus 0.40 times 0.30 times 0.01, like that. And then finally, the last way to get to this would be to go through that. So you would go through that branch and that branch like that. So that last probability would be 0.60 times 0.005 like that. So again, when you're doing the probability tree, you're figuring out what are the 3 routes you have to go to get to defective. So you go this route, this route or that route. Okay, then you're going to just multiply this out and then you'll get your probabilities. Okay, so I'll do this like this now. So I'm going to go 0.4 times 0.7 times 0.015. I'll record just each of these things as we go. So the first thing is 0.0042. The second part would be 0.4 times 0.3 and then times 0.01. So that would end up giving plus 0.0012. These are all real low probabilities of the onboard computers being defective. That's what you would want as a business. Then the last one is 0.6 times 0.005. So that will give 0.003. And then you just add these things up. Okay. So let me add those up. We would have 0.0042 added to 0.0012 plus 0.003, and then that would answer the question. So you would end up getting 0.0084 would be the final answer of that problem. Okay, that's how you do your probability trees given some scenario like that. So that would be your final answer right there. Okay. Okay. All right, that's the final answer. Okay. All right, so any questions about that? All righty. Okay, so let's push on here and let's see what we're doing here. So next page, we're going to talk, I've just taken an example out of the book to show you the difference between a situation where you have without replacement versus when you have with replacement. Okay, so let me just kind of go over this one right here. This one just basically says you have a bag and you have this. You have 3 balls are blue and you have 2 balls are white. So if it's without replacement, it goes like this. The probability of getting a white on the first draw would be 2 out of 5. The probability of getting a blue on the first draw would be 3 out of 5. Okay, now if the probability, now let's just assume we take a white out. So if you take a white out, which we do there, then the probability of getting a white on the second draw would be 1 out of 4, say. The probability of getting a blue now would be 3 out of 4. Okay, that's without replace. That means first draw was white, we take it out. Okay, let's assume on the first draw we got a blue. So we take it out and we don't put it back in. Then your probabilities go like this. The probability of white is 2/4. So that's where that comes from. Probability of blue is also 2/4. Okay. So this is kind of what you would do on this then, is you would do this. So if you wanted to find the probabilities like this, each branch would go like this. You would multiply these probabilities. So if you multiplied 2/5 times 1/4, you would get 0.10. If you did 2/5 times 3/4, you get 0.30. If you do the probability of 3/5 and 2/4, you get 0.30. And then this branch would be 3/5 and 2/4. So let's say we want to find the probability of a white on the second draw. And this is without replacement. So you would have to look at these 2 branches. You'd have to go that way, or you would have to go this way. Okay, so that would be the way you would do this probability is you would do 2/5 times 1/4. And then the other way to get to the white on the second draw would be to go through 3/5 and 2/4. Okay, so if we did this out, and we did this earlier, I think that's 2/20 plus 6/20. So that's an 8/20 probability. And if you wanted to do that on the calculator, you get 0.40. You can also look at this tree diagram. It's just kind of like, okay, that's 0.10 that way and 0.30 that way. So it adds up to 0.40, see. Okay, so you can do that like that. So what I want to do is I want to talk about what with replacement would be like. So again, at the very beginning, you have a 2/5 probability of getting white, and you have a 3/5 probability of getting blue. So that's where those come from. That's the same as it is in this tree diagram. Now, let's assume that we got a white on the first draw. Well, what this means is you got a white, You took it out, but then you put it back in. So with replacement. Now the probability of getting a white is still 2/5, and the probability of getting a blue is 3/5. So notice that's different there. Okay, things didn't change. All right, so that's what that means with replacement, see. All right, and let's say that you got a blue on the first. So what you would do is you would take out the blue, and then you would put it back in. That's with replacement. So you would end up having this. The probability of white is 2/5. Probability of blue is 3/5. So see, the tree diagram on that second draw is different because of the with replacement. Now let's do the probability of getting a white on the second draw. You may or may not get the same answer. It just sort of depends on this. So if we were going to get a white on the second draw, you would have to go either that route or that route. Those would be the two ways to get there. So this way would be 2/5 times 2/5. Okay, and then this way would be 3/5 times 2/5. So you would get 4 out of 25 plus 6 out of 25. So that would be 10 out of 25. Okay, well, that's still 0.40. Okay, so what you'd end up getting is the same answer, and that's just a coincidence. It doesn't have to be that way. Okay, if you did different probabilities, then it might give some different answers. It just sort of depends on the situation and what you're looking at. Okay, all right. Okay, so that's the difference between the two situations with and without replacement. All right, the next thing I want to look at is what we mean by independence and how we compute these things. So first of all, the definition is if A and B are any events in a sample space S, A and B are independent if this happens. So if the probability of the intersection is just the probability of the product of the two events, then we say it's independent. Otherwise, they're dependent. Okay, so we'll talk about what that is. Theorem 2 says if A and B are independent events with non-zero probabilities in a sample space, then we would expect, if they're independent, then we would expect the probability of A given B to just be probability of A, and the probability of B given A just to be probability of B. Okay, so I'm going to explain how this goes in some examples here, how you can make sense of this. Okay, so let's see. The idea on this example 5 here, I read the problem. It says, in two tosses of a single fair coin, we're going to show that the events A, a head on first toss, and a head on second toss are independent. So the first thing we're going to do is, in figuring out if they're independent or not, is let's write down what the sample space is. Now, you could do a tree diagram, but it's not really necessary on this. If you toss two coins, I'll just go ahead and do it. You have head, tail on the first, head, tail on the second. So there's 4 things that can happen. You could have a head, head. You get 2 heads. You could get a a head, then a tail, not a hail. Okay, then a tail, then a head. Then tail, tail. I'm writing and thinking and talking at the same time. Sometimes I do funny things like that. Okay, so anyway, what are the 2 events? The first event we're going to call A. That would be you get a head on the first toss. So let's list out what that is. If we get a head on the first toss, out of this sample space, it would either be head, head, or head, tail. So that would be the 2 events of getting a head on the first toss. Okay, the other one is a head on the second toss. Okay, so we're going to do that. We're going to look at this. The head on the second toss would either be the head, head, or head on the second would be a tail, head. So there's 2 events out of the 4 possibilities. That's a head on the second toss. So we're going to see if they're independent or not. Okay, so what we have to do then is we have to figure out, we have to basically just check this and see if this is true. So we have to check the equation probability A given B, we want to see if that's equal to the probability of A times the probability of B. If it is, then they're independent. If not, then they're dependent. Okay, so we're going to do that. Okay, well, let's just do these. The probability of A, that would be ahead on the first toss. There's two possibilities to get ahead on the first toss, so that would be a 2/4 probability. So I'm just going to reduce that down to 1/2. The probability of event B happening would be ahead on the second toss, so that would either be this one or this one. So that is, again, a 2/4 probability, so that's 1/2. And then we got to figure out the probability of A intersect B. So if you look at the intersection of these two events, getting ahead on the first toss and getting ahead on the second toss, the overlap is one place. So the head-head is the overlap, so that means that probability would be 1 out of 4. Okay, so that is there's only one possibility of getting ahead on the first and ahead on the second at the same time. So now we check our calculations. The probability of A intersect B is 1/4. The probability of A is 1/2. The probability of B is 1/2, just see if it works or not. So that would be 1/4 equals 1/4. So we would say, yes, these events are independent of each other, okay? So that would be the idea with that. That's how you verify that, all right? Okay, now we're going to look at, a couple more of these things, just kind of look at different scenarios on this, okay? I'm going to get the card diagram. Okay, so we're going to do a couple of examples that have cards in it. So again, what we're doing is we're drawing a single card in a 52-card deck. We're going to see if these two events are independent or not. So we're going to look at the card drawn as a spade. We're going to look at the card drawn as a face card. So what I'm going to do is we're going to figure out these three probabilities. To test for independence, we got to figure out the probability of drawing a spade. We have to figure out the probability of drawing a face card. Then we have to find the probability of the intersection. Okay, then we'll check that equation. Okay, so the first thing is probability of a spade. Okay, how many spades are in a deck? 13 are in a deck, so that would be a 13 out of 52 probability. Now you can reduce that fraction, and don't forget you can reduce fractions on your calculator if you have to, so I'll just review how to do that. You would go 5/13, get a decimal, and then you can go math 5/13. Why did I do that? 13 out of 52, get a decimal, convert to a fraction, so that's 1/4. Okay, so we have a 1/4 probability like that when we reduce that. Okay, now the next thing is the probability of a face card. So the face cards are these. Okay, there are 12 face cards in a deck, so that means this is a 12 out of 52 probability. Okay, so we can reduce that. I'm just going to do this on the calculator. I'll be lazy. So I'm going to go 12 over 52, get a decimal, math, fraction, that is a 3/13 probability like that then. Okay, so let's just kind of reduce these as we go. So that's 3/13. Now the probability of an intersection. So if you look at what I highlighted in yellow, so I highlighted all of these things. Those are all the spades. Then I highlighted all of the face cards. So what's in common? Well, these are the ones that are in common. So there's 3 cards that are spades and face cards at the same time. So that means this would be a 3 out of 52 probability. Okay, so you want to figure out those 3 probabilities. Now this is what you test. You look at the equation, probability of E intersect F. You see if that's equal to the probability of E multiplied by the probability of F. Okay, so we've already got this. This is 3 out of 52. The probability of E was 1/4. The probability of F was 3/13. See if you get the same thing. Okay, so what you would get on this one then is you would get the same thing here. So this is 3 out of 52. This would also be 3 out of 52. So that would be yes, these two events are independent. Okay, so whenever I ask you for whether two sets are independent, you have to do those three probabilities and see if the product of the probabilities is the same as the probability of the intersection. Okay, all right, it's actually pretty simple as long as you can count. That's what I keep saying. That's what probability is all about, is can you count correctly, right? And do you know which formula to apply in which situation primarily? Okay, so now we're going to look at the event of drawing a club and the event of drawing a heart and see if they're independent or not. Okay, so what we're going to do is we're going to do the probability of getting a club. We're going to do the probability of getting a heart. Then we're going to do the probability of the intersection of those two sets. Okay, so to begin with, let's do the probability of a club. So what's the probability of a club? Okay, that's 13 out of 52. Okay, I'm going to reduce that fraction. You could use your calculator. That gives 1/4. Okay, the probability of a heart, what is that? Okay, see, there's something a little bit different going on this one now. So the probability of a heart is 13 out of 52, which is also 1/4. Okay, well, what is the probability of the intersection? In other words, what's the intersection of is there any card that's a club and heart at the same time? No. So that probability is 0 out of 52, so it's 0. So again, what you do is you test to see if the probability of the intersection of these two sets is the same as the product of the probabilities of those two events happening. So this is 0. This is 1/4. That's 1/4, true or false? Now that's false. Therefore, we would say they are not independent. Or you can say they're dependent. Okay, so that would be the answer on that, is they are dependent or they're not independent. So that's the idea. Okay, so let's see. Let me give you a couple of problems to do and see if you got this nailed or not. So I'm going to bring us down here, let you pause the video and just do these two problems. These are about cards, so you can refer to my card diagram if you'd like. Okay, so if you want to check, this is what you should have got. If you did this correctly, you would have got problem number 1. These are examples of independent events. And problem 2 is they're not independent, so they are dependent. Okay, so again on this one, you had to figure out the probability of a red card. So there are, in this case, there are 26 red cards. So therefore, that is a 26 out of 52 probability. That reduces to 1/2. Okay, the probability of being divisible by 5 would be these cards here, either the 5 or the 10, like that. Okay, so there are 8 of those cards, so that would be 8 out of 52, which will reduce to 2/13. Okay, the intersection, if you look at the intersection where the yellow and blue overlap, they overlap in 4 places. So in other words, half of those cards that are divisible by 5, 4 of the 8 are red. Okay, so that would be a 4 out of 52 probability like that. And that reduces to a 13th. So what we do is we test to see that the probability of the intersection, which is 1/13, equals the probability of the first event, 1/2, times probability of second event, 2/13. Yeah, they are, because the 2's cross out, so you would get 1/13. Okay, so it's a matter of applying that formula. Okay, let's see on this next one that I had you do. Then it goes like this. So this says the first event is a king. So what is the probability of getting a king? Okay, it's 4 out of 52, so it's 1 out of 13. There's 4 kings in a deck of 52. Okay, the next thing is the probability of a queen. So there's 4 out of 52 there, so it's also 1/13. And then the intersection. Can a card be a queen and king at the same time? No, it can't. So the intersection is empty, so that would be 0. So again, you're testing to see that the intersection's probability is the same as the product of those two probabilities. 0 is not equal to 1 over 13 times 1 over 13, so it's not independent. Okay, you don't have, so that would be how you would figure in those individual probabilities then, okay? All right, okay, so let's move to the last page here, and this is just a summary, so I'm not going to really go over these things, but what we talked about in this section is the conditional probability formulas. We talked about the product rule. That's how you do an AND probability when you have a given probability, and how to test for independence. Okay, like that. Those are the three main things that you want to know in that section. Okay, so I'll close this up. That'll wrap that up. Hopefully you'll do fine with everything on this section.